Hey guys, welcome back. Miss Miller here, missing you all. We started talking about exponential functions. Today we're moving into exponential growth and decay, which we dived into a little bit with exponential functions, and we talked about this table, which we're going to move in here and remember what happened on that table. But like exponential functions, the exponent is a variable. So the little baby number that goes on top is a variable. It's got to be X, Y, Z, some sort of letter goes up there. Now, some examples of exponential growth and decay. You probably think of it and you probably heard of different things, but like bacteria, it grows exponentially. Savings accounts. When you were in 7th grade and you kind of talked about simple and compound interest. Well, compound interest has the formula t power. So as you can see, it's in the exponent. The formula has it to the exponent, so it's growing exponentially if you have compound interest. So those are some real life examples of how you would see exponential growth and decay in a real life scenario. So again, we're going to do this table that we talked about. I'm going to label these boxes so we can talk about the boxes and you know what boxes I'm talking about. Okay, so if A is positive and B is greater than 1, we're going up like this. If it's positive and B is between 0 and 1, so it's a fraction, it's a decimal of 0.3, 1/2, 1/3, something like that, it's going this way. That was beautiful. If B is greater than 1 and it's negative, we're just flipping it over. It's going this way. And if A is negative and B is between 0 and 1, it's going this way. So the questions ask, which graph is growing? Which one's growing? Well, obviously, if you were to think about x and y axis, and we were talking about a positive slope of a linear equation, would be going this way. Same thing with an exponential. Exponential, is one that's growing this way. It's going up. When I get further along on my x-axis, I'm also going up on my y-axis. So like if I'm at 1 here, I'm here. If I go to 2 though, I'm going up even more. So it's growing. So an example would be graph 1. Which one is decaying? Well, same thing as linear. Same thing as linear. If I had a graph, well, negative linear equation's going this way, right? Nice negative. Same thing with an exponential. It's coming and going down this way. Same direction. As I move farther along this way on my x, I'm going down on my y. So that would be graph 2. Graph 2. So what we came to our conclusion, if B is greater than 1, then the graph is growing. If B is greater than 1, the graph is growing. And the graph of the exponential growth equation goes up like that. It's got that curve. If B is between 0 and 1, then it's decreasing, which makes sense, right? Even with linear, if I multiply by something greater than 1, it's going to get bigger. Less than 1, it's going to get smaller. And it's going to look like this. It's going down. Those are kind of bad lines. So let's go through the steps of how to look at this. So step 1, is it exponential growth or exponential decay. And remember the way to do this, it's growth. Oops. It's growth if b is greater than 1. It's decay if b is between 0 and 1. That's how we figured that out. Then you were to identify A, the initial amount. So if we're talking about a deposit, a savings account, the initial amount would be how much I put into my account. So we have to identify A. Then identify the R, the rate at which it's growing or decaying. It's in a decimal form. So always remember that growth, exponential growth / decay is written as a rate. Oops, can't spell. Is written as a rate, which is a percent. Then it wants to identify B, the growth factor, which is either 1 plus R or 1 minus R. 1 plus R if it's growth, 1 minus R if it's a decay. And then X is your time. So those are our steps. So let's look at number 1 and see if we can go through these steps to figure this one out. It says the value of a car is $21,500. It loses 12% of its value every year. Well, this word loses already tells me that it's going to be going down. It's going to be a decay. It's going to be a decay. This is A. It's the amount I put in, right? It's the amount I have to pay. $21,500. That's how much I have to pay. And if you remember, the formula for exponential function is y equals A times B to the x power. So, I'm going to plug in my A. I know what my A is. So I've got y, I guess I'm writing it down here. Y equals A, which instead of A, I'm putting 21,500, times B. Now this is the tricky part. If you remember over here, if I can find it, B is the growth factor. So I'm either doing 1 plus R or 1 minus R. Well, R, it told me the rate is written as a percent. R is 12%. So I'm doing 1 minus my R, because we're losing 1 minus, and 12% is not a number. And remember, in order to change a percent into a fraction, you can either move the decimal place over 2 times, or you're taking 12 divided by 100. And when you do that, you get 0.12. Either way. So 1 minus 0.12, and then to the t power. We don't know what it is. We don't know what t is. It just tells us after t years. So to the t power. And if you wanted to simplify this, we could simplify this part in here, right? We know what 1 minus 0.12 is. So you could simplify this even further if you would like, and you would get y equals 21,500 times 1 minus 0.12 is 0.88 to the t power. Either one of these works. It then asks us to graph the function. I think the best way would be to make a table. So I would make a table of my x and y values. And again, this time t is my x. And I would just plug it into my calculator or Desmos. And I would just plug in, like, what happens when I plug in 1 for x or 1 for t? Well, I get 1,000 or 18,920. If I plug in 2, I get 16,649.6. 3, I get 14,000, 651.648. 4, 12,893.45024. 5, I get 11,346. It's not a 6. 0.2362112. Okay, so as you can see, we're exponentially decaying. Like I'm going from 18,000, almost 19,000, way down to 16,000 to 14,000, 12,000. So it's going down. If I were to make my X and Y axis, one, two, three, four, five. And we'll just say, let's just go from 5,000, 10,000, 15,000, 20,000. So if you look at 1, I'm at almost 19,000. So when I go, I'm going to go over 1 up to 19,000. 2, I'm at 16,649. So a little above this. 3, I'm at 14,000. So say about here. 4, I'm at 12. 5, I'm at 11. So as you can see, it's kind of coming down, and it's going to keep going down this way, and it's going to keep going up that way. Not the best drawing in the world. And it's going to get super, super close to this x-axis here, but it's never going to touch it. It's going to get super, super close. This is the asymptote. Remember, y equals 0 is your asymptote, which is the answer to the next question. But if you look, y equals 0 is the asymptote. And that's telling us the value of the car will never be 0. Which makes sense. The car is always going to hold some sort of value. It's not going to hold $21,500 value, but you can always resell it to get more. It also wants us to identify the domain and range of the function. So, domain, range. And remember, Dollar, the robot. Domain is left to right. So if I look on my graph, can I draw a line of how far left it goes? Can I do that? Now, technically, for this scenario, you can. With real life scenarios, you can, because our x-axis is representing time in years. Can I have negative years? No, I can only have positive. So the lowest amount of years I could have would be 0. So it's got to be greater than or equal to 0, because I can't have negative time. But then I could go all the way to infinity the other way. So technically, this graph, it would keep going. But since it's a real life scenario, it does not go past the y-axis, because time cannot be negative. Range, on the other hand, let's look. Range is robot, bottom to top. So the bottom line, well, it's never going to cross here. It's never going to have a 0 value. That's one of our asymptotes. So it can't be 0, so I'm not including. Notice I don't have an equal sign underneath. And it can go all the way to infinity. It can go all the way up this way. It could keep going up as far as it wanted. So that's domain and range. And it wants us to estimate the value of the car in 6 years. So I'm using the formula I was given, y equals 21,500.88 to the t power. But instead of t, I'm putting 6 6. So then again, I would plug this into Desmos or your graphing calculator, and in 6 years the estimation of the car value is $9,984.69 after you plug it into your calculator. How do we feel? Sweet. Okay, so let's look at these practice problems down here. It says identify the function as growth or decay function, the initial amount, A, the rate of growth or decay, R, as a percent, and evaluate the function when t equals 5. Round your answer to the nearest hundredths place. So, growth or decay. Remember, growth or decay, if you look back over here at our steps, is if b is greater than 1, it's a growth, or if b is between 0 and 1, it's a decay. So I'm looking, b is the growth factor. It's 1 plus r or 1 minus r. So if we look at these scenarios, I've got 1 plus 0.16. So this is a growth because it has this plus sign here. It's a growth. There we go. The initial amount, A, this is A, would be 300. The rate is what I'm either adding or subtracting. So in this case, it's 0.16, but it wants it as a percent. So instead of 0.16, let's move the decimal back over and change it back into 16%. And it says when t equals 5. So I'm taking my equation it gave me, y equals 300, 1 plus 0.16, and instead of t here, I'm going to change it to 5. And when you plug that in your calculator, you get 630.10. So not too bad. Let's look at number next. Growth or decay. Well, this one, it doesn't give us, it gives us the simplified version here. We want to know, what is it adding or subtracting? Well, if it's 1.15, it's over 1, so I'm obviously adding, and it's always 1 here, so I'm obviously adding 0.15. That's another way to write it. So, since I'm adding, the addition sign tells me that it's growth. The initial amount I put in is A, which is 800. Growth rate, right here, 0.15, and again we want to change that to the percentage, 15%. And then we're going to plug in y equals 800, 1.15 t, but instead of t, we're going to plug in 5. And when you plug that into your calculator, you get 1,609.09. Hopefully you're feeling good so far. It's really not too bad. This is stuff you've been doing, just with a few more steps added. Okay, let's look at number next. Again, this one didn't have a 1 plus or minus, so I want to rewrite it this way. And remember, f of t is just a fancy way of saying y equals. So if that confuses you, change it to y. 57. Now, since this number is less than 1, I know that I took 1 and I subtracted something. Well, 1 minus what gives me 0.77? Or 0.77 plus what gives me 1? 0.23 into the t power. So since I'm subtracting here, I know that it is a decay this time. Because I'm subtracting, I know that it's a decay. The initial amount, A, is right there, is 57. The rate is 0.23, and again we want to write it as a percent, so 23%. And then we're just plugging in y equals 57 times 0.77 t, and instead of t we're plugging in 5. And when you plug that in your calculator, you get 15.43. And that's how you analyze functions of exponential growth and decay. So let's look at number 7. This time we have to write the problem. So the value of a piece of jewelry is $280 and decreases at a rate of 3% yearly for 7 years. Well, this decreases tells me that it's going to be a decay. That's what that tells me. This is the initial value of it. The A equals 280. And then it gives me the rate as a percent of 3%. Or when I plug that into a problem, I can't plug in 3%. So if I move the decimal over 2 spots, I get 0.03. And it also gives me a time of 7 years. So when I go to plug this in, I know my formula is going to look something like this. Y equals A times 1. Since it is decay, I know I'm subtracting, minus whatever my rate is to the t power. Well, I know what all that is. I'm just going to plug in now. We said A was 280. We said my rate was 0.03 and my time was 7. So when I go to plug all this in, I've got oops, let me go back here. Y equals 280, 1 minus 0.03. Again, you can't just plug in 3%. 3% is not a number. You've got to change it to a number. And to the t power of 7. And when you plug this into Desmos, you get 226.24-ish. I'm rounding to the nearest hundredth again because this is moolah. So in 7 years, it's going to have a price of $226.24. Let's try number next. The value of a movie poster is increasing at a rate of 3.5%. In 1990, the poster was worth $20.25. So the initial amount was $20.25. Find the value of the poster in 2013. So it says here it's increasing. So this already tells me that it is an exponential growth, not a decay. I know that A is $20.25. I know the rate is 3.5%. If I move it over, I get 0.035. The time, it wants to know from 1990 to 2013. So to get time, I've got to do 2013 minus 1990. So when you get that, you get 23 years. So the time is going to be 23. Well, let's go to plug in now. Again, I'm a step person, so I'm going to write my formula out. Y equals A. 1, this time, since it's growth, it's going to be a plus, whatever R is, to the t power. And then I'm just going to go in and I'm going to plug in what I got for A, what I got for R, and what I got for t. And when I do that, I get Y equals 20.25. 1 plus, again, I have to plug in the actual number, 0.035 to the t power of 23. And when I plug that into my calculator or Desmos, I get 44.67-ish. So the worth of the movie poster is going to be $44.67 because it's going up, which makes sense. So always check if your answer makes sense. It's increasing, so if you get a number that's less than what you started with, you did something wrong. So always check yourself and figure out if your if it makes sense. Okay, number 9. The population of a town is represented by the function f of x, remember it's just a fancy way of saying y, equals 112,396 times 1.13 to the x power. What was the initial population of the town? Well, initial is the number right here. So the initial population of the town was 1,012,396. Is the population increasing or decreasing, and by how much? Well, if you look at this, remember, I've got to write 1 plus or 1 minus something. This can be written as 1, and if I'm above 1, that means I'm adding, and I've got to add the 0.13. So I know because it is adding, because I'm adding, it is increasing. And it's increasing by 0.13 or 13%. And it wants to know, when will the population reach 15,000? So we want to plug in 150,000, my bad. So we want to plug in 150,000 for y, because that's the population. 1, 1, 2, 3, 9, 6, 1, 3, x. So once you get this, I would graph it on Desmos, or you could start plugging in numbers here to figure out when it's going to be a population of 150,000. And so when you graph it or you start plugging in numbers, you're going to realize it's between 2 and 3 years. 2 and 3 years. Okay, number last, we're almost there. Thanks for staying with me if you've been listening to this whole thing. Y'all are awesome. The population of a town is decreasing. So, decreasing at a rate of 7%. In 2005, there were 1,600 people. So, there's my initial. Complete the table below and the graph. So, when I go to write my equation, I've got y equals 1 minus, because I'm decreasing, 7%, so 0.07, and then to whatever the t power you want. So in 2005, we're at 2005, that's 0 years. We haven't gone any. But if I jump, because we started at 2005. So if I'm at 2005, I've gone 0 years. 2006, I've gone 1 year. 2007, 2. 2008, 3. 2009, 4. 2010, 5. 2011, 6. 2012, 7. 2013, 8. And here's what I would do. I would go to Desmos. I would go to your calculator and do it. I would plug in the, I would plug in the year here and see what you get. So when you plug it into either Desmos or your calculator, in year 0, obviously, we're at 16,000. That's where we started. Or 1,600, sorry. 1, we're at 1,712. 1,832, 1,960, 2,097, 2,244, 2,401, 2,569, 2,749. And again, all I did was either you can go to y equals in your calculator, plug that in and hit second graph and look at this part and it'll do the table for you. Or you can do it on Desmos, and if I need to do a Desmos tutorial, y'all just email me or message me on Google Classroom, and I'll be more than happy to do that. But that's fine. So then we go to graph. So let's say 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I'm going to count by 300, 600, 900, 1,200, 1,500, 1,800, 2,100, 2,400, 2,700, and 3,000. So at 1, we're at 1,600. So I'm about here. Whoops, that's at 0. At 1, I'm at 1,600-ish. Oh, no, I did it right. Y'all gotta keep me in check. This is why I miss y'all. Y'all can always keep me in check. 0, I'm at 1,600. 1, I'm at 1,712. 2, I'm at 1,832. 3, I'm at 1,960. And I'm just going to graph. Let's go over here to 827. So as you can see, it's doing this. It's going up. There is our graph in our table. And again, plug it into y equals or Desmos to get your table. You have a practice problems to do. Remember, those are not a grade. Those are for you to ask me about because I cannot help you with your assignment. Your assignment is due next Tuesday, or the 7th, at 11:59. Okay, good luck. Let me know if you need anything. Bye, y'all.